Thank you for the kind introduction, and thanks for having me here. So I'm excited to be part of this event. Can everybody hear me okay? This sounds a little weird from back here. Okay, very good. So I've been working on machine learning for a long time, and maybe 20 years or so, and it sometimes amazes me what people bring to production with machine learning. And I asked myself the question recently, how can we possibly trust these machine learning machines? And so today I'll talk a little bit about that. But I'll start with how I got into this journey. And so, my clickers. So if you talked to me a couple years ago about machine learning, I said, yeah, I know a lot about machine learning. I've been teaching for a while. It's pretty easy. You start with some data. Then you run some fancy machine learning algorithm. Then what I do next is show you that my curve is better than your curve, and I publish a paper about it. But this is not why I got into machine learning in the first place. I got into machine learning because I wanted to make killer robots. I read a lot of sci-fi, and I thought I'd build some really intelligent things that were going to change the world. And the exciting thing is, over the last year or so, we've seen, and before, but we've seen these things come to tremendous amount of reality. You see industry after industry being disrupted by companies that build what I call intelligent applications, which are differentiated by machine learning at their core. So in the early days, you can think about Amazon with retail and recommendations, or Google with advertising, all the way to how Uber dispatches its taxis. And that's disrupting a really interesting industry right there. So this idea, this sci-fi, is really coming to reality today. And in fact, I believe that within 5 years, every successful, innovative application is going to use machine learning at its core. It's going to be intelligent. And in fact, if you're not intelligent, your application is not going to succeed. So our goal is to really accelerate the process of creating such applications. And we've talked to a lot of people where we've seen a lot of value come from machine learning. So areas like recommender systems, targeting, advertising, lead scoring, fraud, and many others. But what is well known is, for example, if you take Netflix, which is well known that 70% of their views come from recommendations. It's pretty exciting. They're famous for spending about $200 million a year on the recommendation team. And so very few companies are able to do that kind of investment. And in fact, as we talked to a number of different companies and innovators, we saw 3 core big blockers that stop folks from building these intelligent applications. First is, how do you map the business task that you want to solve to the machine learning problem you need to solve underneath? So it's well known, for example, that for recommenders, you need something called matrix factorization. And you can find that in a textbook and everything. But getting to that requires a lot of expertise and knowledge and background, which slows down the rate of progress. Now, after you find out that, okay, I'm going to do a matrix factorization model, there's still a lot of iteration and interaction that goes on. You have to do feature engineering, you have to combine different models, you have to optimize, and that process can be time-consuming and clearly not some of the most exciting things that we do in our every day. And finally, if you're thinking about taking these things to production, you have to build systems that manage and deploy these algorithms as real-time services that your applications go and query. And usually, everything's custom built. So a data scientist or a developer will write, say, a prototype in Python or R, and they'll typically throw it over the fence, and some other team will re-implement that in Java 6 to 12 months later, and the thing that gets implemented has nothing to do with the thing that they thought they were building. So these are real pains, and real pains are slowing down progress. And so as we think about us, this sort of talk a little bit about what we're trying to do at Dato. We're trying to help folks first create value fast. Even if you don't have a machine learning background, can you build that first churn predictor, lead scoring system, recommender fraud system as quickly as possible? But not as a black box that you can't change or edit or modify, something that gives you flexibility to be highly innovative. And they can make it easy to take that thing to production, to build intelligent systems in production. So these are 3 core tenets: get it to value fast, having flexibility to innovate, and building intelligence to production. So that's what we've been doing. And our goal is to accelerate innovators who want to create intelligent applications using what I call agile machine learning. So let me give you a couple examples of really fun little applications that we've built. And these applications, they fulfill 2 pain points that I was having in my life. The first one is my sister is a fashion designer, which makes buying gifts for her a really high bar process. And so I wanted to buy her a dress, and if I do a keyword search for dresses on basically any website, you get a wide variety of dresses. They have different styles. It's hard to figure out which one is right for her. I do know that she likes floral dresses, but if I just search keyword floral dress, still there's a lot of alternatives. And it's hard to nail down which one is right for her. Now, what is more natural for me as an experience is to look at one that maybe looks visually interesting or looks visually appealing for what I know she likes, and then find other dresses that get recommended to me that are visually similar to that one. So for example, if I find that this dress here is one that I think she's going to like, can we find dresses that look similar? Now what we did in this example is use a deep learning model that analyzes the features of this image and then finds other dresses that are visually similar to this one. So if I click on this floral dress, you see that you find other dresses that look kind of like it. It's actually pretty cool. But maybe I say that my sister, she likes something that's a little stylish and different, maybe something with multiple patterns, so maybe I'll get her this one, and you see other dresses where you have interesting patterns inside them. But maybe I've gone too far here, maybe something a little more in between. This one looks really cool, and the model even looks like my sister. So that's perfect. Now, this is not a kind of demo. You're welcome to try it out. You can come and play with it, and you'll see that it really provides really interesting, cool recommendations. And I can click on anything here. Here's a dress I don't think I've clicked on before, say this one here, and you'll see that it finds visually similar ones. It's pretty impressive. There's no shopping experience like this today, but I wish there were. And what I've been thinking about for a while, and the team at Dato has invested in it, is how do you enable a developer without machine learning background to build something like this in a few lines of code? So if I click on this little gear, you'll see that the data that we're using is images of dresses and the text description. I haven't gone and talked to you about the text part, but this part of this demo also uses text. But in a few lines of code, we can do keywords extractions inside the text. A few lines of code of Python, we can build a deep neural network to analyze those images. And basically, with one line of code, we can take that and deploys a real-time service on AWS, such that every time I click on an image, let's say this one, it gets shipped off to AWS, goes through a GPU, it comes back for prediction of other dress you might want. And that's what I would like to enable anybody to build. So this is an example of a kind of application you might want to build. Here's another one that was bugging me. We have a 2-year-old, and it turns out that when you have a kid, you have to buy a lot of stuff. And if you think about baby monitors, you cannot have a child without a baby monitor, it turns out. I don't know how civilization ever got built. And so there's a lot of variety, and many of them with tons of reviews. It's impossible for me to really understand how one differs from others, or which way one baby monitor might be better than other. And here's two that have very different prices. Can I understand a little bit of in what aspects they differ? So what we did behind the scenes here in this little example is to do text analysis on the reviews and find different aspects that differentiate the two products. So here, range, battery life, signal, and so on. And for each aspect, I can dig in and get a sense of what people are saying positively and negatively about that aspect. So here's a fancier baby monitor, but it seems like the signal is not so good in terms of the sentiment of the reviews. Let's see what people are saying positively or negatively about the signal. So here's the most negative sentence. It has to do with the wireless signal of this baby monitor. And it's hard to read from the back, so I'm going to read it to you. It says, if nothing else in your home sends out wireless signal, then this will work very well. But then again, it's 2014, and who doesn't have wireless signal in their home? So that seems like a problem. And if you read this other one here, it says basically, if the signal has to go through any walls at all, then this is not a baby monitor for you. So clearly not one I want to buy. And it would have been hard for me to dig up those reviews and those aspects without having some kind of machine learning algorithm going through the 1,000 or so reviews for me. So that's the kind of creativity that I think we can empower, and we can empower those folks who can be way more creative than we are at building such applications. So that's the goal. That's the goal for us. And we've been doing this for a couple years now, but we've been doing actively over the last year. And it's been really an exciting journey to go from academia to taking these ideas into the real world. And now we have a large number of customers that are building really cool and innovative applications that use machine learning. So here's a really fun example. Scripps Network is a large media company. They own HGTV, Food Network, and other properties. And our champion, Josh, is a database BI guy who didn't know anything about machine learning, was in a budget meeting for the next year, and saw they were paying people to manually label 500,000 images, and then wanted to scale that. And he said, oh, I heard this AI thing is pretty cool. Can I do something about it? And he found us on the web, downloaded the product, started using it, built his first image tagging system. And that's really important because about $150 million of revenue for their site comes from ads. And if you have better image tagging, you can place better ads. And so he was really excited about that and started building multiple applications, including a cool one, ingredient substitution tool for a Food Network. So if there's a recipe, they use a screen, but in the reviews, everybody says, oh, you should use yogurt, it's healthier. It automatically bubbles up yogurt as a substitute for cream. So over 4 months, he started building multiple applications, having impact, and he now has a team of people working on this and has become director of data science for Scripps Network, which is pretty cool. Nice journey there. We've been growing a community. I was going to plug in, I hope that's okay, the Data Science Summit in July. There's also one in Israel that we're running, where you'll see great speakers also, just like here, and you'll have access to lots of people talking about machine learning, ranging from folks at Dato to industry leaders like Jeff Dean, and Jeff Dean from Google, Daphne Kohler from Coursera, and many others. And I'll talk about this a little bit later. We've also been building an online education program with 6 courses in machine learning that is done very different than any other machine learning course out there. So I'll talk about that towards the end. So our goal, as we step back, is to accelerate this journey of building intelligent applications. And before I talk about trust, I want to talk a little bit about what that journey looks like and show you a little demo of that. So we built 3 products, one to create applications using machine learning, GraphLab Create, one to scale, Dato Distributed, one to deploy as a service called Dato Predictive Services. But really the way we think about it is you want to build an intelligent application like that dress demo, and you want to rapidly build and prototype things on your laptop, and the question is, what is the right architecture to build such applications? And the one that we've invested in very heavily is what we call the microservices architecture, where every model that you build can be easily packaged and deployed as a real-time service that an application should query. And then based on the feedback, so for example, did the user click on a particular dress or not, we can close the feedback loop and actively improve the performance of the model through live monitoring and online learning. And so this closed loop system is something that you have to build if you want to be really successful with machine learning in production. So, and we can run on whatever infrastructure that you want out there. So let me show you an example of building a recommender system, just like we talked about Netflix, and how you can do that in a few lines of code, where a lot of the things underneath can be automated for you but you also have the power to go and edit, choose your own algorithm or add your own method. So let me show you a quick demo of that. So here's my quick demo. This is an IPython notebook, Jupyter notebook. It's just a nice way to demo things. But underlying this, I'm going to show you a machine learning library. It's called GraphLab Create. So I'm going to type import GraphLab, and it's going to get it started. And we're going to use some San Francisco restaurant reviews from Yelp. So this brings me back to my days living in the Bay Area and trying to find great places to go to. And so here's what restaurant review data looks like. You have a particular restaurant where a user provided a rating, there was a price range, a type of food, there was a review they wrote, the date, and so on. And normally, you have to slice and dice that data in order to understand first and kind of explore and understand what that data looks like, and that takes a while. And so we created, because we're slowing us down, we created this little visualization tool that we call Canvas that allows you to quickly get a sense of your data. So what's going to happen here is with calling Canvas, we do a sketching algorithm where for each column, we provide one pass sketch of what is in there. So for example, you see that the most popular restaurant for Yelp's reviews is Pizzeria Delfina. Yes? Good choice. Most commonly reviewed food is breakfast and brunch. That was a little surprising to me. And clearly, $2 signs is where it's at. And so that gives me a sense of the data. Let's say that I feel pretty good about my data. I want to go ahead and build a recommender system. So here, we provide the ability to choose your own recommender system like factorization machines and so on. But if you just type GraphLab recommender.create, we automatically select the right algorithm for your data, optimize it, and build something. So here I'm running on my laptop, and it just finished, and we have a recommender system built. And you can do all sorts of things with it. You could evaluate it. You can query it. I'm just going to show a quick evaluation. So as I was saying earlier, I'm not a coffee drinker, but lots of people in my team are. So when I come here, I heard that 4 Barrel Coffee is a great place for coffee. What other places should I take my team? Any suggestion? Okay, let's see what the recommender system says. Side Class Coffee, Ritual, Blue Bottle, Coffee Bar, and Phil's. The first two, as I understand it, have the similar don't roast your coffee too much and the nouveau coffee thing, but yeah, it looks pretty good. Now, I'm more of like a amnesia kind of guy. Yes? No? Yes? Yeah. Yeah, so we know what we're talking about. Some dive bars in the Mission. So go to Amnesia, listen to some live music on Wednesday night. When I go somewhere else, where else should I go? Okay, for a few more. Anybody more? So let's see what the recommender says. Casanova Lounge, Dalva, Elbow Room. I think somebody mentioned Elbow Room over there. Is it pretty good? Dive bars, places I could try. So in a few lines of code, we got something that seems to give reasonable predictions. Let's say that I trust this model, and we'll come back to trust in a little bit, and I want to deploy this as a service. Normally, I'd have to take this, package it, and hand it over to somebody else to build a real-time service that my front end could query. Instead, we're going to show you that you can do that really easily. So the first thing that I'm doing here is connecting to a deployment that I already have, so I'm not starting the deployment myself. Here's one that there is on AWS. And if I do a .show on it, you'll see that there are 3 machines. They're all live. There are many models that are being hosted there, so many microservices, and they're all versioned and providing different capabilities. So what I'm going to do now is take the model and wrap it with a Python function. So this I'm showing you GraphLab create models, but it could be anything. It could be scikit-learn model. It could be anything that you create. I'm just wrapping a Python function. And when I do that, and I'm going to add it to my deployment, it collects all the dependencies, packages it up, pickles that, sends it over to AWS, and starts hosting as a service. Depends on how fast the network is, but it's usually pretty fast. So the pickled object is copied to S3. Those 3 machines are then going to read them from S3 and start hosting that as a robust real-time service. So now we should be done, and now I can query it. So I'm going to, you can query it from JavaScript, you can query it from curl. Here I'm going to query it from Python, and I'm going to give it as input the restaurant name 4-Barrel Coffee, and it gives me back a JSON response that includes site glass, ritual coffee roasters, and others. And the interesting thing, or one interesting thing, it also has this unique query ID so that the front end can provide a feedback loop to say, for this particular query, the user clicked on 4-Barrel Coffee, and that's used to update the model in a closed loop, or to do A/B testing, or to do bandits. So all those things are possible. All right, so this is how we think about that journey from exploring the data to building a model to deploying it as a real-time service. Oops. Now, as I said in the beginning, the question is, can I really trust the model I just built? Can I really think that this is the right thing for me? And I call this the trust challenge. We typically will go from data to building a machine learning model, maybe iterating over that, to deploying predictions the front-end application is going to serve. The question for me is this model really working the way I hope it's working? And can I convince myself, my engineering boss, my business boss, they were now all going to get fired because of what I just did? And how do I do that? So I'm glad, my student Marco Ribeiro and my postdoc Samir Singh have been working, this is the University of Washington, have been working on some really interesting algorithms and methods to explain the predictions of any machine learning technique. And we have a paper on it that's pretty exciting that you're welcome to check out. So I'm going to tell you a little bit about this. And since everybody signed the release form on the way in, right, we can do a user study. So we're going to start with a user study. Thank you for participating. Let's say that I built a deep learning model to solve a very important task. Given an image, I want to know whether this is an image of a wolf or a husky. Now, we're at the University of Washington. This decision is extremely important, right? Some people know why. Husky is the university mascot. They always bring a husky to the stadium. You don't want to bring a wolf and you know what's going to happen right there. So we're going to use a deep learning model to protect ourselves from liability. And so I tried this model. You see the predicted value on the top here, and you see the true value. And for everyone, let's say for a vast majority of the test cases, it gets them right. Let's say for this one, it got it wrong. Seems pretty good. My question to you, user study question is, do you trust this model?
It's predicting the snow in the background.
Ooh. Anybody else? So that is a good suggestion. So what deep learning models are really hard to understand. It's hard to know whether or not to trust them. And so what Marco Samir did is come up with a way to, for any algorithm, go back and try to understand what features or what part of the data was most important to making the decision. If you look at this problem and you highlight for each image what part of the data was most important to make the decision, you'll see something very interesting, as was pointed out over here. If you look at the wolf pictures, it's not predicting based on the features of the wolf, but so you don't have a wolf detector, you have a very, very fancy and deep snow detector. And so understanding trust can make a huge amount of difference. Here's another example. There's the famous 20 Newsgroups Dataset in text. Anybody heard of this dataset? Yeah. So this data set collects articles posted in 20 news groups. Anybody know what news group is? They later called forums, later called Facebook pages. What's that? Yeah, so news groups kind of this thing is amazing where you can post articles and other people read them. And so there's this classic data set where you're trying to predict based on the text of the article, which news group is it from? Is it from politics? Is it from religion? And so on. And it was a known problem where we always use an example in class because basically any modern machine learning model gets really high accuracy, like 94% accuracy on that. And so Marco and Samir tried out their approach on this to try to explain why we're getting such high accuracy. And they learned something really interesting. The reason that most models get really high accuracy on the training Newsgroups data set is that they're using features like the email address of the person who posted the article. And John at gmail.com always posts in politics a news group. And so extremely misleading and not generalizable results. If you remove that kind of data, you get much lower accuracy, only 57%. So what seemed to be an amazing success of machine learning turns out to be a relative failure in some ways. So the idea here is, when you create a model, can you trust the model before you deploy it? And this is important. It's important for the accuracy issues that we discussed. It's important, say, in Netflix, so users understand and you gain some transparency of why a particular movie was recommended to you. And it's really important in some domains like medicine. So if you tell a doctor, probability this patient has cancer is 95%, the chances that the doctor uses anything of that information is 0. They're going to just ignore it. But if you say, look at this patient, look at this MRI results, look at this other related cases, look at this paper that just appeared in the New England Journal of Medicine, now you understand why this patient is likely to have cancer. So trust has many different impacts, and it's important to model and understand it. So Marco and Samir created a system that allows you to understand and visualize why a prediction is made. So here's an example of the email address being used in 20 news groups. And I won't go into the details of the algorithm, but just as a highlight, what I do is try to explain the key features that were used to make the prediction by computing explanations that are good for a particular prediction. They might not be good for the whole space because there might not be a single explanation that shows why a deep learning model works. But for this particular image, you can explain really well. And then they have a technique using some modular function optimization that explains the model as a whole. They created a really cool visualization tool and did a lot of user experiments to show that, user studies that show that this idea makes a big difference. And here's a really cool user study. Take that 20 news groups data set where if you don't clean the data, you only get 57% accuracy. And so, okay. So the way that so the way that Marco wanted to do this is he cleaned the data himself really well and came up with what he called the gold standard. The idea is, if you clean the data, what is the best possible result that he could get? And the question he was asking is, can mechanical Turkers, by looking at explanations, knowing nothing about machine learning, help refine the model, crossing out things that they think that shouldn't be relevant in that explanation? Can they get close to Marco's gold standard? And so the question is, after multiple rounds of mechanical Turkers, how close can we get to Marco's gold standard? And what he found out is that the mechanical Turkers, after 3 rounds, do better than the gold standard that he created. So I fired him. Just a joke. Marco's an amazing student. But it was pretty impressive that even people that don't have a machine learning background, when faced with explanations, can understand how reasoning should be done and can help improve the performance of a machine learning algorithm. And so for me, building trust in models is not just about evaluations, here's my accuracy number, although you want to make that easy and clear. But it is about being able to explore and understand the predictions of a model like we did with floor barrel coffee, and having explanations that help us understand why a decision is being made, and is that decision made for the right reasons. And this can have impact not just in the performance of the algorithm, but in other aspects of the real world. I mentioned the doctors. Here's something that at Dato we've done with explanations is having quite a lot of impact. So if you think about churn prediction, I'm trying to decide whether or not the user is likely to churn. You can get a probability to stop using your service. You can get a probability of churn, and you can try to explain why in general people tend to churn. But you can do some things that are much more interesting with explanations. So you can segment the users based on the ones that are likely to churn for the same reasons. And then you can provide human understandable reasons of why the algorithm thinks this particular category of users is likely to churn. And then marketing person can take that and do targeted campaigns that help them address those folks. So for example, there could be a category of users who was shopping a lot in the section of the website that had to do with toddlers. 2 years later, they stopped shopping. That tells me something about those users and tell me something about what kinds of things they might be open to in terms of campaigns. So explanations can have a tremendous amount of impact, and it's something that we've been working on quite a lot, both from the academic perspective and from the company perspective. Okay, so I'm going to take, there's a few minutes left, so I'm going to take a few minutes to talk about two things. A little bit about what are the technology we've been invested in, because these are kind of general, visible concepts that are useful throughout the machine learning space, and a little bit about what we're doing with online education at Coursera. So in terms of technology, we've been building something called GraphLab Create that has a number of automatically optimized algorithms at the top, like recommender system I showed earlier, churn prediction, lead scoring, sentiment analysis, and others, which are backed by 50 or more highly optimized machine learning algorithms for tasks like regression, classification, and others, and based on a data layer called the S-frame, which is highly optimized for machine learning. So I'll talk a little bit more about talk a little bit more about S-frames in a second, but S-frame is really super cool. It's an open source package we created. It's an out-of-core data frame so that even on your laptop, you could deal with hundreds of gigabytes or even terabytes of data at interactive speeds. A big thing for us is to make it easy to deploy what you build as intelligent microservices. So let's say that you're building a real-time recommendation system or a real-time fraud detection system. Some of our users do. Like every time you do a credit card transaction, I want to predict within 7 milliseconds whether that transaction is fraudulent or not. So the way that we do it is allow folks to create any models in Dato, in R, in Python, Java, and others, and deploy them as services that can be consumed by the real applications that are written in Python, JavaScript, or whatever they're written in, just through REST APIs. And this is a really fast system. So based on requirements from some folks in the ad space, we've optimized it so that you can get round trips within 5 milliseconds to make about 100 queries for boosted tree models. And you can do about 1,000 such predictions per second, even on a single AWS machine. A big thing for us for certain machine learning tasks is to scale them in a distributed way. So this ranges from, for some algorithms like boosted trees, providing large-scale distributed implementations, and for other tasks like selecting parameters in machine learning models and searching over parameters, where it's more of a data parallel task, being able to do that really easily. So this is what Dato Distributed does. It can run on whatever infrastructure you have. It can be AWS, it can be Docker, it can be a Spark cluster, and provides you the ability to do this distributed machine learning algorithm. So here's an example of the performance that we get. If you take the benchmark Criteo dataset, which is an ad targeting type of question, if you look at the distributed boosted trees work way faster than any of the alternatives out there. And if you look at graph data, which is something that we've been working on for a long time, we can deal with graphs that basically nobody else can deal. So here's the famous common crawl graph, which has 100 billion edges. This could not be finished on any other system out there at the time, and you can run it off on a single machine because S-frame is an auto-core infrastructure, but you can get really fast as you scale to more and more machines. So this is a little bit about the tools that we've built. At the University of Washington, we also work a lot on education, especially now on online education for machine learning. So with Emily Fox, we've created a new machine learning specialization on Coursera. People know Coursera, yeah? Online education platform. So Emily and I are creating a 6-course machine learning specialization there, which is built quite differently than any others in the space. So I've been teaching machine learning for a long, long, long time, and I and every other course that I've known in the past follows this following recipe. Start with the probability of a coin flip and how you infer that from data, and then build up from there. And hopefully by the end of the course, of the end of the semester, you say, oh, and there's some applications for machine learning. Go figure them out yourself. With Emily, we thought there has to be a better way to do this, and the way we're doing it is starting from use cases down. So we start with questions like, how does Zillow predict your house price? And then we deconstruct that to say, this is what regression is, and this is how you estimate that from data. How does Pandora figure out what song you want to listen to next? And from there, we deconstruct it. We talk about recommender systems, and we talk about things like matrix factorization and so on. So it's a use case-based approach. In the first course, we focus mainly on the use cases themselves. So if you think about building a machine learning pipeline, it goes from data to the machine learning method to intelligence, let's say. You have to figure out what machine learning task you're solving, what the models are, and what the parameters of those models are, and what the optimization algorithms are. They're going to select the parameters, and then how to evaluate these things, whether they're giving the results you're hoping. So we take the models and algorithms as a black box in the first course and just focus on what are the use cases, what are the tasks, and how do you evaluate and deploy it and make sure it works. And then in the subsequent courses, we dig in and the students will implement their own algorithms and their own techniques from scratch for these different areas. Now that they use cases on real data for every single one of these. So it's a very hands-on, real data-driven approach. So the first course on regression, second on classification, the second course on regression, third classification, the fourth on clustering retrieval. Then there's one matrix factorization, dimensionality reduction, and then the final capstone project is extremely cool. Folks are going to build deep learning models that combine text and image data and deploy them as services. So that's how we're thinking about a new way of learning machine learning. So I'm super excited about the space. I hope you can tell. And the phase transition I see today is that we've gone from just an academic, purely abstract, cute thing, my curve is better than your curve, to intelligent applications that are changing the world. So if you saw, for example, Google's announcements yesterday, I'm sure everybody was just busy here and didn't see anything, but it's pretty cool. You know, personal assistance and AI is now talked in the media everywhere, and that's extremely exciting. And it's possible for Google to have tremendous advances, but what's going to really spark creativity is if every developer in the proverbial garage, which could be the literal garage, or it could be the project inside a massive company, is able to quickly and creatively build intelligent applications that use machine learning at the core. And so my single mission here is to accelerate that process and to help go through the creation process, gaining trust, and deploying these machine learning services. Thank you very much. I don't know if we take a question or not take a question. I saw a hand over here. By the way, I have a super bright light in my eye, so I see shadows, so don't get upset if I... Oh. Yeah, I think a hand here.
I have two questions. Number one, the one you showed, the machine learning after 3 rounds actually performed better than your student. That was actually testing with the same data, or actually add more test samples to evaluate accuracy?
So here's how the experiment was set up. The model was trained on the 20 Newsgroups Dataset with the features that the mechanical Turkish thought were bad being removed. And the models were tested on a held out dataset that mechanical Turkish didn't get to see, which was not from the 20 Newsgroups, where it was recently extracted news articles so forum posts from today. 20 Newsgroups is from the 90s. This is from today.
Okay, great. Second, you actually tuned my appetite up, but you didn't explain how actually your technology, what kind of technology you use to be able to explain how we should trust the machine learning conclusion.
Yeah, so I did not go into the details of the algorithm. I kind of hinted in that one slide, and it's really a question of time here and depth. And I'll point you to the paper to look at it, it's easy for you to find. But here's basically what we do. We take an input, we perturb it, meaning we change the features here and there, and then we build what's called a locally weighted model. So it's a model that is weighted around this data point, and it is trying to be good for this particular data point, not everywhere in the space. And it's trained on the perturbed data, and then it tries to figure out what are the key features to differentiate what the model thinks is positive versus negative, or one class versus the other, or whatever, around the perturbed data for the current input. And it's a simple, explainable model. That's the goal.
But that means the person must know the underneath math.
They don't have to know the math. When I showed you the deep learning problem, I forget who over here just knew already my punchline and just blurted it out, it was the first time, actually, I've done this talk for a long time. But if you look at the second example, everybody, I hope, got the punchline. And you didn't have to know anything about machine learning to look at it and say, snow is not a wolf. It's true that snow is correlated with wolf. Wolves maybe live in snow or go to snow some of the time, but snow is not a wolf. And so that kind of understanding can be done by mechanical Turkers, as we saw in the mechanical Turk experiment. I think there's another question. I neither see you.
Yes, sorry. Thank you. Very interesting, Carlos. You say the title is Trusting Machine Learning. How about trusting the people who are using the platform or the models they are building? What's the antidote for that issue, if any?
So your question, just to be clear, is do I trust the app developer that consumes the machine learning predictions? Is that true? Yes. Okay. I think it is my responsibility as a data scientist to work with those people or to provide a system that is robust to the way they use it. It's easy for us to say, this doesn't work because Joe or Mary over there who built the front end screwed it up. And I think that that's a responsibility we cannot assign to them. And so I think it is important for us to provide enough transparency, ways to evaluate the model, clarity, and so on. And it's a journey. I don't know that we can do it today, such that those people, those folks can be super successful. So if you think about database systems, we've done quite a good job over the last 30 plus years of providing abstractions and feedback that makes it easy for most developers to consume and use a database and understand when things are going right and wrong, more or less. And for machine learning, there's a long journey ahead. So I think, sorry to be like a little direct here, but I think it's absolutely our responsibility to figure out how to do that and how to help those folks use it the best way they can. Yeah, that's my view.
Thank you very much.
Thank you.